Hello everyone, welcome to Advanced Microcontroller Systems, Elec 3310. Today we're studying Chapter 8, Section 9, and the subject of H-bridge. A group of engineers came to FSU and asked if our students can build circuits to operate actuators. And our answer, of course, we can, and now we received a grant from NASA to create 3 different techniques to operate not only actuators but DC motors. Of course, we got to match the interface to the motor. There might be some extra work there at times. But this study that we're doing today will discuss H-bridges. And H-bridge is an electronic circuit that can change the polarity of a DC motor. We're going to use modules and shields for our techniques discussed, but H-bridges can be built using discrete components. An H-bridge is a circuit that can reverse the polarity to a DC motor, and we're using electric DC actuators that utilize a DC motor. So we know that reversing the voltage polarity to a DC motor will reverse the direction. Also, if we reduce the voltage, it'll lower the speed or reduce the speed. And to do that, we will use pulse width modulation. We won't do it with this first technique, but we will do it with other techniques. I want to go over this schematic that's on the screen here. So we know that the DC motor can be reversed by simply reversing the voltage polarity. With S1 and S4 closed and S2 and S3 open, we know that the polarity on the left side of the motor goes up to positive VCC and the right side of the motor goes to the return line or ground. Now, if we open S1 and S4 and close S2 and S3, we essentially reverse that direction. Reverse the polarity that's on the motor and also reverse the direction of the motor. There's many methods to construct an H-bridge. We're going to discuss 3 techniques. In today's part 1, we're going to discuss using relays. So for our relay choice and to develop an H-bridge, we're using a module. And this module has 2 relays on board. And the specs on our module says 10 amps for 250 volts AC and 15 amps for 125 volts AC loads. And but we have DC that we want to supply and there's nothing written on there. Well, if we had to choose, we would choose the RMS voltage or current here of the lowest setting, which would be around 7 amps. However, if we look at similar modules, similar to the ones we're using, what they state on theirs is 10 amps for up to 250 volts AC and 10 amps for up to 30 volts DC. So those are things to be aware of as you develop your specs. And I did make measurements on my system, so I know how much current it draws. We'll talk about that. So here's our relay board. And so the relay board is going to take voltage, DC voltage here from an external source, and it's going to take that voltage and switch it to the actuator and switch the polarity depending on which relay is activated. So let's look at the left side here. We have the center common contact that goes to the actuator, and the same with the second relay. We notice that the normally open contacts of this relay is connected to the normally open contact of the other relay, and the normally closed contact of this relay is connected to the normally closed contact of that relay. And we have on this right side we have the microcontroller connections. We have VCC, which is 5 volts, and we have ground from the microcontroller, and we have pins 9 and 10. Pin 9 is connected to N2 and pin 10 is connected to N1. And it's important to tie together the grounds of both power supplies. The power supply of the external 12 volts and the microcontroller 5 volts. So the grounds are connected together. Why? To give a common ground. Here is the schematic of our two relay module. We notice that the inputs at N1 and N2 activate the Optical Isolator, and this is the Optical Isolator here. Sometimes those are called optocouplers, photocouplers, or optical isolators, so there's different terms. But this device will isolate the microcontroller from the relay board, and it basically uses light to do that. So when we ground the diode at either N1 or N2, right here, when we ground those, what happens is that the optocouplers U1 and U2 will light, and the lighting of the optocoupler will turn on the phototransistor. So here's U1 and U2. There's the phototransistor. This is internal inside that integrated circuit. So the phototransistor, once it's activated, will send VCC to the base of the NPN transistor. So it'll turn on Q1. This action will activate the relay coils by providing ground. So if we see this, we got VCC, and then we'll provide ground once we turn on that transistor. And what that will do is allow this relay coil to be energized. When this is energized, this normally closed contact from 1 to 2 will change from 1 to 3. This is the actuator we're using. Well, this is just a picture of an actuator. And the actuator we are using, here's the specs. We're using a progressive automation actuator. This is the model number. It's a 12-volt DC motor internal within that actuator. And it's got a 12-inch stroke, which means that this rod will extend 1 foot. And it can move a force of 330 pounds, which is quite extensive. We're going to use on our board an infrared sensor or receiver, and this is the way we connect it. VCC, as this infrared receiver is pointing towards us, VCC is on the right, ground's in the middle, and the signal pin is on the left side. The signal pin will be connected to pin 11, the microcontroller, and this is the IR receiver we're using. The microcontroller is going to interpret the code from the remote control that's sent, and once that signal is sent to the microcontroller, it'll decode which button was pressed by the hexadecimal number that it's interpreting when you press that. Each one of these will represent a different hex number. And here's our circuit showing our relay module and showing the power going to the actuators. And so we're connecting here, and we're using that light Optical Isolator to isolate our circuit between the relay and the actuator and the 12-volt circuit to the microcontroller. And on this microcontroller, we're using an Arduino Uno. So the microcontroller is going to interpret the code and will perform a specific function per the instructions of the C++ software that has been converted to machine code. And that machine code is embedded into the double EEPROM on the microcontroller board. So all these instructions will include whatever the user wants from pressing the remote control. It can turn on LEDs, can move actuators, it could do both. And here's a summary of the connections between the components used on our system. So a little bit about the C++ code. We're using a universal infrared code reader for the infrared devices. And we found it at github.com. So here's the address of that, www.github.com. And with that, we had to add the library file called irremote.h to our C++ program and include that in our code. So the program provides a hex code for each button on the IR remote, which we use to make something happen, like move the actuator or turn the LEDs on or off. And these are the steps we took. So here's a snippet of code, and what we're doing is we're reusing software, and that's a common thing that's used nowadays. And what it does for us when we reuse software is to provide a good way to start the project very quickly and to see if the project is worth extending our effort. And you can get things up and running very quickly, but if you're going to use this code in your production, then a thorough review of the entire program is required. But I want to go through a little bit of this code. As we talked about, a digital low will activate the relay. So we have to identify the pins that are connected to the specific places of the relay module and LEDs. And here's some of the hex code I was talking about. There's this would be something on the remote control that's labeled this way, and it will give this hex code when it's sent to the infrared receiver and decoded by the microcontroller. And there's other codes for other buttons on that remote control. Now, because we're using digital write in our C++ code, we have to set it as an output, and we do that. And this is all done before our serial begin at 9600 baud rate. So here is our loop that repeats indefinitely, and what it does is it decodes the hex number and determines which code was pressed, which button was pressed. And so if a certain button was pressed, it's going to do certain tasks, such as turn on a green light, extend the actuator. And so that's turning on relay 2, but turning off relay 1. And we do that, we turn it on with a low, like we talked about at that relay module board, and we turn it off with a high. So we're forcing it on or off. And when we want to shut things down, this is the procedure we'll use. We press a different button for that. And then if we want it to retract, we reverse the polarity. And this is the technique we use. So this is the setup we have. We have the power supply here. We got the actuator. We got the microcontroller. We got a breadboard with LEDs and our infrared sensor on here. And we got our 2 relay module board. Well, thank you. That's all we have for today. That's the Relay H bridge. Thank you.